Okay, welcome to my channel. In this video, I am going to explain traveling salesperson problem. So, in this traveling salesperson problem, we will see the basic information and basic method, and after that, I will explain example under traveling salesperson problem. First of all, I will tell you what is traveling salesperson problem. As normal salesperson, generally, if you see the salesperson, those who are roaming in villages, they are moving in villages and they may sell some goods. Okay, so they will start at their own place. They will start at their own place or their own village or their own station or workshop, and they go to all the villages. So they may have target, their own target. Either they want to visit the 10 villages or 20 villages or 10 streets or 20 streets. But finally, after selling the goods at the evening time, they must reach again at their own place. Is it clear? That is the target. So, like the salespersons, here we are applying the same concept on examples, and we can solve the problem, and finally we get the optimal solutions. So, generally, this particular problem is coming under dynamic programming. Okay. So, by using dynamic programming, we can calculate optimal solutions. Optimal solution or optimal path, the optimal path which is covered by the salesperson to sell all the goods or items. Is it clear? So, before going to see the example, I will tell you three examples, three basic examples under traveling salesperson problem. One is postal van problem or postal van example. One is postal van example. Okay, so we know generally postal van starts at post office. If we treat post office as one node, this is post office, and the aim of postal van is moving around the street or village, that particular village or town. Okay, it must collect the mails or postcards or post mails at each and every post box. Okay, na? Suppose if now n number of post boxes are there, postal van ultimate aim is it must start at post office. It must move to it must visit all the post boxes and collecting all the mails from post boxes, and finally depositing it post office again. Okay, na? If you treat post office as one node and all the remaining post boxes as n different nodes, and we can construct a graph with n plus 1 nodes. One node is post office and remaining nodes are represented with the post boxes. Okay, finally we can connect one graph. Okay, na? But what is the ultimate aim under traveling salesperson problem or under dynamic programming is, okay, na, this postal van visiting each and every post box, and finally which reaches post office again. So whatever the total distance that is covered by postal van, that must be reduced. That must be minimum. So that's why this example is related to distance. Okay, so postal van example is related to distance. The aim is starting at post office and visiting all the post boxes which are coming under this particular post office, and collecting the mails and depositing all the collected mails at post office again. So that's why the ultimate aim under this particular example is reducing the total distance that is covered by the postal van. Okay, na? So that's why this example is related to distance. I will tell you two more examples, and one example is related to time and another example is related to cost. Okay, na? So time example is, suppose if you take a robo arm, if you use robo arm for tightening the nuts. Here we are using robo arm for tightening the nuts on machinery, any machinery, okay, or circular machinery, let us assume circular machinery. So it starts at first nut, and which tighten that particular nut, and which goes to next nut, like that. It must tighten all the nuts. It must tighten all the nuts on the machinery. So here we need to concentrate on how much time is required to tighten all the nuts by using robo arm. Okay, so according to this traveling salesperson problem or dynamic programming, so here we are relating this example with time. So the total time which is required by the robo arm for tightening the nuts must be reduced, means minimum. So this example is related to time. Okay, so first example is related to distance. Ultimate aim is we need to reduce the total distance required by the postal van to collect all the mails and deposit those mails at post office. If this example is robo arm, here we are using robo arm for tightening the nuts on machinery. So here the total time required by the robo arm for tightening the nut must be minimum. Okay, na? So that's why this is related to time. And third one is related to cost. Because at any situation, at any location, or at any basic item, we can apply traveling salesperson problem or dynamic programming. Okay, so third one is cost related. Cost related means suppose if you use the machinery, if you use machinery for producing the items or commodities. Items or commodities. Please remember here we are using same setup. Same setup of machinery. Same setup of machinery. Here we are performing this production cyclic way. Cyclic manner. Here we are producing all the goods in cyclic manner. At each cycle we are going to produce n different items. So first cycle we are producing n items, and second cycle also we are producing same n items from item 1 to item n. Item 1 to item n we are going to produce. That is the aim of this particular machinery. But with this slight addition or subtraction, because initially machinery started with m different devices. M devices. Okay, na? So with m devices, machinery is producing item 1, item type 1. For producing item type 2, either one device replacement is required, or one device removal is required, or one device addition may be required. Okay, with that particular change, we can produce second item type. So like that. Okay, na? But what is the aim here? Here some change over cost is required. Machinery setup 1 to machinery setup 2 for producing item type 2. Okay, some change is required on machinery. So that change over cost must be reduced. So ultimate aim is we need to produce n different items at each cycle, but the same number of items we are going to produce at each cycle, that n items, n different items. So item to item, either we need to add some extra devices or removing extra devices is required. Okay. So ultimate aim under this particular example is the change over cost is required now. So changing machinery setup 1 to machinery setup 2 for producing item type 2, and machinery setup 2 to machinery setup 3 for producing item 3. Like that, machinery setup n-1 to machinery setup n for producing nth item. Okay. So some change over cost is required. The change over cost may be reduced by removing the device from the machinery setup, or cost may be increased by including extra device into the machinery setup. So that's why the change over cost must be reduced under this particular example. So like this we can take all the examples, all the related examples, and we can solve these examples by using dynamic programming. That's to under traveling salesperson problem. Now I am going to take one example with one simple graph, and I will explain how we can solve or how we can calculate optimal path using traveling salesperson problem. So in that particular graph, the nodes may be cities, or nodes may be other items like nuts, or nodes may be post boxes, or you can consider any item as node number. But ultimate aim is here we are going to calculate the optimal path from source node to all the remaining nodes, and again finally reach to source node, because the traveling salesperson problem ultimate aim is calculating optimal tour here. What do you mean by tour? Tour is circular path. So here in this example, if you see, the postal van starts at post office and visiting or covering all the post boxes which are coming under this post office, and finally the postal van must reach the same post office. Okay, so here the number of nodes involved are n+1 including post office, but finally the postal van is producing circular path. Okay, this particular circular path is called as tour now. Okay, na? So ultimate aim of traveling salesperson problem is to produce optimal tour and optimal tour for any problem. So for calculating optimal tour, we have one basic or simple equation, that is we should start at, let us assume first node is postal van. We should start at postal van, and we visit, the postal van should visit all the remaining nodes. See here, we are subtracting 1 from this vertices set. Okay, visiting all the nodes and finally reaching postal van. So G is treated as path cost. So this is path cost. Okay, na? So once postal van starts at post office, we don't know whether postal van immediately reaches second post box, third post, or second node, third node, fourth node, or nth node in this particular graph or diagram. Okay, na? So that's why we are taking k here, but that too we are going to extract minimum. So here we are varying k from 2 to n. Number of nodes in the particular graph may be n. Okay, na? Starting at first node and visiting all the remaining nodes by considering one by one node and forming this particular equation. But out of all this, we need to select min. Okay, na? So once you select second node, now from second node, what about the path of the remaining nodes from second node? So from and again consider third node and calculate path cost from third node to all the remaining nodes except the first node and third node, like that. We need to repeat this expression, but why we are using this is here all the items are unknown. Okay, now of course this may be the edge cost. We can get this edge cost from this particular example or any example, but this one is unknown value. So that's why for calculating all the intermediate values, we supposed to use this particular expression. Okay, now here this is set of vertices. That's why we are directly taking set as S. So I is not included in S like K. Okay, now so G of I comma S equal to minimum of all the vertices. We need to consider all the vertices which are belonging to S. So J belongs to S, C like K, J belongs to S, Cij plus G of J comma the remaining nodes. So from I if we reach K, like from 1 if we reach K, like that from I if we reach J in S, J must be belonging to S and I must be doesn't belong to S. So Gij, now consider each and every node as J, okay na, and go to that particular J and calculate the path cost from J to all the remaining nodes and again to J. Okay, so that's why we are taking G as G is used for calculating path cost and Ciz is edge cost. So for calculating all the intermediate nodes, we are using Z of I comma J. Once after calculating all the intermediate nodes and substituting those intermediate nodes in further expressions, because while solving problem you get idea. Okay, and finally we get original solution at this particular location. Okay, na? So this equation is producing final value. Here the set size is n minus 1. Okay, na? Here if we expand set size is n minus 1, we get set size values are n minus 2. Again this is unknown, we need to expand this. If we expand it, we get set size as n minus 3, n minus 4, so on. So if we directly use this particular equation and expanding it and keeping all the unknown values at one moment, it is better start with the lowest level. Means set size 0. Start from set size 0 and calculate all the set size 0 values, means set size 5, and substitute this set size 0 values in set size 1, substitute set size 1 values in set size 2 and so on, and finally after calculating set size n minus 2, those n minus 2 values are required here. Because this set size is n minus 2. Calculate all the values which are there at n minus 2, set size n minus 2, and substitute those set size n minus 2 at set size n minus 1, we get optimal path cost. Okay, so that's why we are using this particular expression for calculating all the intermediate results. After getting intermediate results, finally we use this particular expression and we get the optimal path cost. Now I am going to utilize these two equations and now take this example. Now we constructed this example based on the postal van and or any other example. Okay, so now assume this may be the postal van example. Now this is post office and these are all the post boxes. Okay, now in this matrix the distances between 1 to 2 and 2 to 1 are given. Here the two-way direction, but paths are not same. So 1 to 2 path is different from 2 to 1, like that. Like that we have the path distances. Okay, now this is direct edge cost. 1 to 2, 2 to 1 edge cost, 2 to 3, 3 to 2 edge cost, and 4 to 1, 4 to 1 to 4 edge cost, and all the edge costs are given. So we cannot directly use first equation. By using second equation, we can calculate all the intermediate results. Okay, na? So that's why we should start with set size equal to 0, means 5. Okay, in set size equal to 0, here actually G of I comma S is there. G of I comma S is there, but the size is 0, means 5. So G of I comma 5 equal to Ci1. Just simply replace 5 with 1. Okay, so other than 1, there are only three other nodes. Once you involve 1 means that is the final calculation. Okay, so that's why involve all the remaining nodes for intermediate results calculation. Now in Z of 2 comma 5, G of 3 comma 5 and Z of 4 comma 5 you are supposed to calculate. What is G of 2 comma 5? G of 2 comma 5 is C21. What is C21? 5. At G of 3 comma 5, C31. What is C31? 6. And G of 4 comma 5 is C41, because 41, all these are edge costs. C41 is 8. Once after getting mod S equal to 0, means number of elements in S equal to 0, now use this particular values which we have calculated at mod S equal to 0 or 5 and substitute them in mod S equal to 1. Substitute them in mod S equal to 1. Here in mod S equal to 1, we need to consider all the possible combinations, all the possible subsets or combinations. Okay, na? So start with 2. Mod S equal to 1. Mod S equal to 1 means the number of nodes which we are considered in set is 1. So 2 combination is 3 and 2 combination is 4, because only 4 nodes are there. Suppose if one more node 5 is there, then take Z of 2 comma 5 also. Okay, na? So calculate Z of I comma S. Now this is I, this is S. So how can we expand Z of I comma S now? Now take the node number in S as Z. So mean of Cij, equation is Cij plus G of J comma S minus J. G of J comma S minus J. Okay na? So see I say I is 2, J is 3 plus G of 3 comma means J comma S minus J. Once you consider this node, there is no other node here. That's why we need to replace S minus J with 5. Because once after subtracting 3 from this set, we get 5 only. Okay. Now this value is available in this matrix because this value is edge cast, and this is available in previous set calculation. So 3 comma 5. See the 3 comma 5 is C31. So substitute C31 and extract C23 from this matrix and calculate the result. So like this, calculate Z of 2 comma 4 and Z of 3 comma 2 and the remaining values 3 comma 2 and 3 comma 4. 4 comma 2 and 4 comma 4. I will show you now how we calculate 4 comma 2, 3 comma 4, 4 comma 2 and 4 comma 3. So once you take all those combinations, that is over at under mod s equal to 1. Okay. Now we are going to use all these values in mod s equal to 2 as substitutions. So remaining values at mod s equal to 1 are G of 3 comma 4. What is G of 3 comma 4? Here set size is 1. We are dealing with set size equal to 1 in this. So 3 comma 4. How can you expand? Now J is 4. So C34 plus G of 4 comma 5. 4. S minus J means S is containing only 4. So S minus 4 means 5 only. Then take 3 4. 3 4 is 12 plus 4 1 is 8. Okay, 4 1 is 8. Then if we add these two numbers, we get 20. So like that, expand the 4 comma 2 and 4 comma 3. What is 4 comma 2? So C42 plus G of 2 comma 5. C42 is 8 plus 2 comma 1 is 2, 1 is 5, 13. So Z of 4 comma 3. So G of 4 comma 3 is C43 Ij plus G of S minus J. S is 3 only, 3 minus 3 is 5. Okay na? Then substitute these two values, 4 3 9 plus 3 1 6. So 15. Okay na? So up to this is mod s equal to 1. So in mod s equal to 1, just we took number of nodes in the set or 1 only. Now I am going to show you how to calculate mod s equal to 2 by using all these 6 calculations. Okay. Okay. So next one is mod s equal to 2. Now set size equal to 2. Okay. Now in set size equal to 2, now we start with 2. Only 2 remaining nodes are there, that is 3 and 4. So we can take only one combination. 2 comma 3 4 only, because set size equal to 2. If you start with 2, if you reach at 2, and what about remaining nodes now? 3 and 4 only. Suppose let us assume one more node is there. If one more node is there, then with starting node as 2, we must take all the combinations. So 3 4, 3 5, 4 5. Then we get 2 more calculations. If one node number is increased, then we get 2 more calculations. But luckily we have only 4 nodes. So if you start at 2 and at mod s equal to 2, set size equal to 2, we get only one pair. That is 3 comma 4. If one more node is there, I have already told the combinations. 3 4, 3 5, 4 5. So like that we need to calculate. So based on number of nodes that are increased, we need to get those number of sets. But here we have only one combination. Now select one node and make it as treat it as J. Now this is I, this is S now. Okay na? Treat one node as J, like this. So C23 plus G of J comma S minus J. Now suppose if you take J as 3, then S minus J, S is 3 4 minus 3. If you 3 and 3 get cancelled, only 4 is remaining. So like this. So C23 plus G of 3 comma 4. If we consider next node as J, then C24 plus G of 4 comma 3. Because S minus 4, S is 3 4, S is 3 4, 3 4. You know the subtraction of set. 3 4 minus 4. Generally, the common values are going to be deleted, and whatever the remaining values in first set, we are considering them as resultant set of subtraction. So like this. Okay na? What is C24? So C24 is 9 plus G of 4 comma 3. Earlier we calculated in mod s equal to 1. G of 4 comma 3 is C of 3 comma 4 is 20. So like that, C24 is 10, G of 4 comma 3 is 15, C23 is 9, C23 is 9, and G of 3 comma 4 is there in earlier calculation. So like this, if you substitute all the values from the previous set, we get 29 and 25. Which is minimum? 25 is minimum. From here onwards, we get the importance of min. Because in previous mod s equal to 1, only one expansion is there, we may directly take that particular value. But here we get two different terms in expansion. So here min is acting role now. Okay, not 25. So G of, if you start with 3, we get only one combination, that is 2 4. I have already told here, if one more node is there, then we get 2 4, 2 5 and 4 5. 3 different combinations we get starting with 3. Okay, na? But we have only 4 nodes. So that's why if you start with 3, then only one combination is there, that is 3 2 4. A same as previous one. Now consider J as 2 and expand it. And next for the next term, consider J as 4 and expand it. Okay, na? So this is I. So Cij plus G of S minus J. So Cij, I is 3, J is 2, and G of J comma S minus J. J is 2 and S minus J is, if 2 is subtracted and 4 is remaining. So like that. And again consider J as 4. So C34 plus G of 4 comma 2. So these two values are available from mod s equal to 1, and these two values are there in this matrix because these are edge cast. This is path cast. Okay, so in the similar way, we can start with 4, and we can take that combination with the remaining nodes as 2, 3 and mod is equal to 2. If one more node is there, I have already told the same explanation applicable here. If one more node is there, 4, 2, 3, 4, 2, 5 and 4, 3, 5. So like that, we need to calculate all the combinations related Z values. Okay, after calculating mod is equal to 2, now we are going to calculate final value at mod is equal to 3 because the 3 is n minus 1. Number of nodes are 4. Once you take mod s as n minus 1, if number of nodes are n, then that will be the final calculation. Then you are supposed to take, at the I place, you are supposed to take 1 as starting node. So only the final values remain, that is at n minus 1. Once you take number of nodes minus 1 stage is reached as mod size of the set, then that will be the final, because here we need to take all the remaining nodes. Then what is accepted here other than s? Only 1. Okay, na? So G of 1, 2, 3, 4 is mod s equal to 3 value, because if number of nodes are 4, then this is the final, because this value is n minus 1. So we will take all the remaining nodes as a set elements and take 1 here as I. So this is I, this is s. So expansion is, now take each and every node as j now. So Cij, I is constant now. Cij plus G of j comma s minus j. J is 2. What is s minus j? 3, 4. Then now consider j as 3. So C13 plus G of 3 comma s minus 3, 2, 4. So C14 plus G of 4 comma s minus 4. Subtract 4 from this, then we get 2, 3 only. So these three values are available at mod s equal to 2. Just extract those values and substitute those values here. And these three values are edge cost values. Those are available in matrix. So C12 is 10, G of 2 comma 3, 4 is 25. So C13 is 15, G of 3 comma 2, 4 is 25. So C14 is 20, Z of 2, 4, 2, 3 is 23. So now add 10 plus 25 is 35, 15 plus 25 is 40, 20 plus 23 is 43. Then which is minimum? 35 is minimum. So whatever the value you get at this particular equation, because this is final application. Final equation, because we are starting with I as 1 and we are taking all the remaining nodes as set elements. Now this is the final calculation. Then whatever the value you get, that value is treated as optimal path cast. Okay, na? So here question is, what is the optimal path now? What is the optimal path now? Just by using simple expression, we can calculate each and every node which is involved in path. So that is, just take j of I comma s, like j of I comma s. J of I comma s is used for calculating or producing optimal path cast. Here j of I comma s is used for returning the node which involvement is reducing the total path length. Okay, na? So j of I comma s is returning one number. That number is node number. Which is involvement, the total length is minimized. Okay. Now start with the final value. So j of 1, 2, 3, 4. What is j of 1, 2, 3, 4? So j of 1, 2, 3, 4 is the node number which involvement is reducing the total path cast. See here we involved 2. From that we got 35. In second expansion we involved 3. From that we got 40. And in the third expansion we involved j as 4. From this we got 43. Then which node involvement is reducing the total path cast? Node 2 involvement is producing total path cast. That's why the immediate next node to be visited from 1 is 2. Next node to be visited from 1 is 2. Now go to mod s equal to 2, because we calculated or we considered the next immediate node from 1 is 2 at mod s equal to n minus 1. Then go to mod s equal to n minus 2, means n minus 1 is 3 here. Then go to mod s equal to 2. There with the starting node 2, because we are already there at 2. Then with the 2, only one combination is there, that is 3, 4. But if one more node is there, I have already told you, na. So 2, 3, 4, 2, 3, 5, 2, 4, 5, like that we get 3 combinations. Out of these 3 combinations, whichever combination is producing minimum, select that particular equation. And in that particular equation, how we got that particular minimum? Either by involving first node or involving second node, we are supposed to select. But here we have only one combination, that is 2, 3, 4. But here, by involving 4, we got minimum value. Even you observe mod s equal to 2, in that mod s equal to 2, the calculation of g of 2, 3, 4, whatever the value you obtain, that particular value is got by involving 4. So that's why Immediate after 2, we are supposed to take node number as 4 in that particular optimal path. Then go to mod is equal to 1 now. At mod is equal to 2, we got next immediate node of 2 is 4. Then go to mod is equal to 1. Go to mod is equal to 1. With 4, with starting with, now currently we are there with 4. Starting with 4, there are two combinations. One is 4 2, another one is 4 1. 2 is already visited. Then we have only one choice, that is j of 4 comma 3 is 3 ultimately. Okay na? Then whatever the which node is visiting, which node is going to be visited next immediate after 4, 3. So we visited all the nodes once only. That is the target. Visiting all the nodes once and finally reach source node now. Source node is 1. We visited in this order 2, 4, 3 and finally we need to reach 1 from the last node visited. Okay. Then 1 to 2, 2 to 4, 4 to 3, 3 to 1 is the optimal path now. Optimal path now. Now what is 1 to 2 edge cast? That is available in matrix. What is 1 to 2? 10. 2 to 4. What is 2 to 4? 10. What is 4 to 3? What is 4 to 3? 9. What is 3 to 1? 3 to 1 is 6. Now these are the edges and the node numbers which are involved in optimal path. If you add these 4 values, that must be equal to 35. So 10 plus 10 plus 9 plus 6, 35. So this 35 is the optimal path of this particular graph, and this is the optimal path cost of this particular graph, and this is the optimal path. So if you immediately, you must reach 2 from 1. After reaching 2, we must visit 4. After visiting 4, you must go to 3, and finally you must reach 1 from 3, because these are the vertices which we have visited in this order, and finally you must reach 1 for completing the path, because our ultimate target is optimizing the tour cost. Tour means circular path. Okay, start at 1 and finally end at 1. That particular tour must end at 1, and visit these 3 nodes in this order. Only we get 35 as the path cost. So like this, we can calculate optimal path cost using traveling salesperson problem for any given graph. Okay, any given graph. Okay, so thank you for watching my video. Thank you so much.